Wonderful. Good afternoon, everyone. Welcome to the Thursday, August 1st HamSCIence Zoom call. This call is sponsored by the HamSci community. We have various speakers from within the community and invited guests to talk on topics of interest to both the space physics community and the amateur radio community, and obviously, hopefully, both. So today we've got a couple of speakers. We're very glad to have Chris Deacon here from the UK to be talking about sporadic E, and Joe Zekovich should be on as well. I say we've got a lot of new people here. It would take quite a while to go through all the names, but I want to welcome everyone. I hope you enjoy listening in and also participate by asking some questions. Chris, I think suggested we ask questions as you go along during your talk, if I recall. Yep. So if there's no objections, I'll just turn it over to Chris and we'll get it started, if that's okay. Go ahead, Chris.
Hi, everybody. So we're leaving enough space for Joe. How long would you want me to stick to?
About a half an hour.
Yeah. Okay. All right. So hello. Some of you will have seen this presentation before, or a version of it at the HamSci conference at Case Western in March. But hopefully this is a slightly more relaxed environment, so we can actually talk about it. As well as simply rattle through slides, and then Nathaniel comes and grabs me and takes me off the stage because I was running over, which is what happened last time. So let me just share my screen, and hopefully you now can see my slides. Yes? No?
Not yet.
You can?
Nope.
No, not yet.
No, we can't.
Oh, yeah.
Oh, okay, fair enough. All right. In that case, let's try that one. Can you see that?
No. Negative.
Nope.
Oh, okay. All right. All right. Let me see here. Sharing the screen. Oh, okay. Fine. How about now?
Yes.
Now we got it.
Now you got it. Okay, good. I was trying to be too clever and get my screen show going before the call, but that didn't work. So let me just put this on screen show then.
Yeah, you're there now.
Great, thank you. So I am a radio amateur. I've been a radio amateur since I was 16 years old. I've been on 6 meters, particularly since the mid 80s, when we got access in the UK. Sporadic E, as we all know, is like, well, many of us know, is the workhorse propagation mode on 6 meters. It's not the same as more conventional F2 propagation. I haven't really got time to go into why it's different and how it's formed in a different way. In fact, if you saw Alex Chartier's presentation 2 or 3 weeks ago, he talked about that a little bit with the wind shear theory and so on. So I just want to talk about where my research is, where it is at the moment and where it's going, having completed the PhD and so on and so forth. So what sort of got me into this was anecdotal stories that one of the things that distinguishes sporadic E is it emerges from nowhere, signals are very unstable, and then they disappear. It's well known for that, and in a more extreme way than if you were on 20 meters. I mean, there's fading on any band where the ionosphere is concerned, but via sporadic E, the higher the frequency you go, the more intermittent it becomes. So I was curious about this. So I put up an antenna with 2 identical Yagis at right angles to each other on the same boom. So a crossed Yagi, like they use for EME or satellite communications, except obviously this is at 6 meters, which people do EME at 6 meters, but it's quite big. It's about 30 feet long. And this is an early observation of mine. It was an SSB signal from Sardinia in Italy to the UK, my station here in the southeast of England. This guy was on SSB, single sideband voice, and hence the gaps in these transmissions here. But you see the graph. So the red is on the vertical antenna. This guy was transmitting horizontal polarization, by the way. So the first thing that you sort of judge from this is, hang on, whereas if I was beaming to the other side of town or even 100 miles away, if I'm transmitting a horizontally polarized signal, it's going to be horizontal pretty much when it gets to the other end. But this, well, it's got a large vertical component for a start. Secondly, the black one, so the red one is the vertical antenna, the black one is the horizontal antenna, and they're fading in a completely different pattern. Sometimes both polarizations fade up and down at the same time, and sometimes they are very different. And effectively what that means is that the effective polarization of the signal at the time, I couldn't measure the phase difference between these two signals, but which would you need to tell you what's really going on. But you could tell that the polarization of the signal was varying on a time scale of sort of seconds and minutes, really. It's sort of 10, 15, 20 seconds, a few minutes, varying pretty constantly. And it's a significant component of the fading that one observes. Of course, most of us have a single polarization antenna, a horizontally polarization antenna. In case you're wondering, the reason why these levels are different is that the noise level was higher on the vertical antenna, which is quite a common thing. So this is curiosity, purely that. Then as I got more involved in it and trying to be scientific about it and make high quality measurements so I could actually be convinced that I was actually right, you know, because it's easy to build quite an edifice of theory on shaky foundations. I realized that actually there's a fundamental question underlying all this. I hope you can see this whole slide, by the way, because I've got various bits of Zoom ironmongery covering parts of the screen, but hopefully you haven't. So most of the time in an ionospheric model, like Velocap or something like that, sporadic key is just ignored. If it is modeled at all, it's usually modeled as if it was a mirror, or it's assumed that it's just scattering, like the hundreds, we call them hundreds and thousands, sprinkles, that you would call them in the US. Or it's the same mode as we get as propagates our signals on 20 meters, 15 meters, 40 meters, whatever. In other words, the signal is bending as the radio wave interacts with the plasma, the partially ionized atmosphere, maybe 1% ionized, and the Earth's magnetic field, and it bends back down and it comes back down. The biggest thing that distinguishes the important characteristics of sporadic key in terms of its effect on radio signals are two. One is this lumpiness, the irregularity. I always think of it as being a bit like a cloud or a duvet, if you like. You could have sporadic key at some intensity spread over a very wide area, but it's denser and thicker in some places than it is in other places. And those places which are denser and thicker are the only ones you're going to, it has to be dense and thick enough to reflect your 6 meter or even your 2 meter signals, as Alex referred to a couple of weeks ago. You're only seeing part of, you're seeing the most intense parts of that duvet. Or blanket or whatever you say. And in fact, if you plot these things out, you see that, you know, that the spread of signals on 10 meters is wider than it is on 6 meters, that is wider than it is on 4 meters, of course, we have in the UK and Europe, or particularly 2 meters. So the question is it like a mirror? Is it scattering or is it bending? And the point is that if it was like a mirror, you transmit a linearly polarized signal, it's going to be linear when it comes back. It might be tilted, but it's going to be linear. Scattering tends to completely lose the polarization. It's unpolarized, like most of the light from the sun is unpolarized, whereas the signals I was observing were clearly strongly polarized. Or it's this magnetoionic. And in the general case, the signal will be elliptically polarized if it's magnetoionic. By the way, that also happens, of course, on the HF bands, on the LF bands. But the effect of it seems to be quite extreme when you're looking at sporadic E on the higher frequencies. They can be very strongly polarized, but changing. So this is the setup that I used. I can answer a question about it if you like. The paper that Gary mentioned in his email about tonight is in fact the one that describes the measurement technique and the care that we had to take, or I had to take, because I was the lead author. And obviously it was all done on my equipment at my house right here. When I said when the signals were the same, I knew they really were the same. The antennas are identical. You compensate for difference in feed lines, attenuation, differences in receiver sensitivity, with a calibration signal from a power, a common source over here, and a dual channel SDR where the two channels are frequency locked or phase locked to each other, and that's actually an ANAN 8000 DLE. The great advantage of doing it this way is that I can grab the I and the Q data, the data that tells me in digital form the amplitude and phase of the incoming signals, and dump it on a disk and then analyze it later. What that allows me to do is to measure, as it says over here, the relative amplitude and phase of those horizontal and vertical components. And what those two antennas are effectively doing is sampling the incoming wavefront. From those, you can calculate, you can transpose the two linear components, orthogonal linearly polarized components, into two circularly polarized components, and describe the properties of the incoming polarization ellipse. So that's what I was doing. So here's an example. Top right there, it's a beacon. I chose to use beacons rather than, for this particular part of the work, rather than general amateur signals, is that they're on all the time and they have usually a significant component of constant carrier, although or they're Morse code, and you can just take out the keying. You've got a constant signal you can work on. So this is the incoming polarization ellipse. It's pseudo real time. It's obviously reconstructed from the digital data, but you can see that the polarization of the incoming signal is constantly changing. The ellipse is elliptical all the time, pretty much. The tilt angle is changing, the angle to the horizontal, in other words, and the width of the ellipse, the ellipticity, the axial ratio, as they call it, which is the ratio of the long axis to the short axis, was also constantly changing. And this particular path is north-south, north Faroe Islands, south to here, over something over 1,000 kilometers. So analyzing that into a histogram, or two histograms on the left there. It's a little crib corner down the bottom right there, which describes the parameters as plotted against the vertical and horizontal axis of the ellipse. So there it is. A is the long axis, B is the short axis, the ratio is ratio one over the other, and that's the angle that you're measuring. So the axial ratio of this particular signal, and this is on over about an hour and 20 minutes, It was a long opening in August 2018. That the first off, axial ratio of a linearly polarized wave. In other words, it's just say that line there. There's no width. So strangely enough, A over B when B is 0, that's infinite. Obviously, I can't plot infinity. And in fact, if there's no, well, anyway, whatever. So this is a logarithmic scale on the bottom. You can see that the signal spends almost all its time in this sort of central region where the ellipse is something like, oh, that's interesting. I seem to have somebody's drawing on my screen, or either that or I'm accidentally drawing on my screen. Okay, so on this side of this graph, it's left hand. On this side of the graph, it's right hand. On these charts, red is left hand, right, blue is right hand. You can see it's swapping from rotating one way circular to, I haven't got time to explain what circular polarization is. I'm sort of guessing you probably know that. And it's flipping from one to the other. It flips at the point that it goes through linear, interestingly. So the point is, this signal was elliptical all the time. And it was predominantly tilted in the top left-hand, bottom right-hand direction. So then if I do the same measurements on a range of different beacons around Europe in as wide a range of directions as I could engineer, which means that there's nothing much across the Atlantic because it's a long way. And also I wanted to stick to single hop sporadic E, one bounce back to the ground, because otherwise you increasingly you don't really have much of an idea of what's going on when you have multiple hops. It could be caudal, it could be all sorts of things. But you don't need to study this all too hard to see that every single one of them, none of them are sitting over at the extremes on these little graphs. They've all got axial ratio, the shape of the ellipse. Circular is in the middle, by the way. As I said, left-hand circular on the left, right-hand circular on the right. They're all elliptical, almost all the time. Now that is what seems to have been accepted in the literature as very strong evidence that what you're looking at here is a magneto-ionic effect. It's the interaction of the wave with the ionization and the Earth's magnetic field. It's not like a mirror. And if you wanted to see a more specific definition of that, you can look at one of the my final paper, which sort of goes to demonstrate that scattering and linear and a pure reflection, which is a sharp boundary, cannot produce the results that are observed. So that's question. The biggest question one was, how does it work? So it's the same mode, the same propagation mode as gives us our signals back on 15 meters or whatever, but it's happening within a very thin sporadic E layer, which might be, typically say 2 kilometers thick. It can be thinner, it can be thicker. And it's, as I say, in blobs. But I'm talking here about the stronger signals, I think, because the only ones I can measure are the ones that last a reasonable length of time. So having demonstrated that, I wanted to explain a few peculiarities that I observed, in particular, that on two very similar paths on multiple days from the beacon in Slovenia, top end of Italy, turn right a bit, and Hungary to the UK on 4 days here and 6 days here. Firstly, actually, the distribution of the shape of the ellipse is very narrow. It sort of sticks around 3:4 to 1 axial ratio in both cases. In other words, it's strongly elliptical, but one is left hand and the other one is right hand. Also, one is tilted one way to the left at the top, the other one is tilted to the right at the top. And why? And if you like, having sort of demonstrated the general principle that it must be magnetoionic, I wanted to still want to try to demonstrate that it's actually consistent with the magnetoionic theory, that it should be like this. So I got into ray trace modeling. I should say, any questions up to that point? Anybody want to? Okay. Various people have used FarLab, and of course there's a and this runs in MATLAB. There is a Python. There's been a port to Python now. They tend to refer to that as PyLab. In order to, if you're going to model polarization in FarLab, you have to use the 3D version. So it's just sort of simple skip distance type of analysis isn't enough. It doesn't tell you what you need to know. The equation that governs, again, I haven't got time to go into now, but the equation that describes the way that radio waves propagate through the ionosphere is the Appleton equation, or the Appleton-Hartree, or I think there's at least two more names that one can add to that, but Appleton's the person who got the most exposure for the theory. What it does is you imagine a whole series of slices of the ionosphere, and it's just like when you put a stick in a pond. It looks bent because the light is going from the air with a refractive index of 1, so basically the speed of light, into a medium which has got a refractive index of 1.5, where the wave travels at a different speed, and that makes it bend away from the incident line. You imagine a whole load of layers in the ionosphere with a slightly different refractive index at every height, because the refractive index depends upon the density of the ionization. The refractive index also depends upon a bunch of other stuff to do with the orientation of the magnetic field and the presence of absorption or not. But what it shows is that a linearly polarized wave most of the time, almost all the time, cannot propagate within the partially ionized plasma that is the ionosphere, because there are only two solutions to this equation, and they're both elliptically polarized. They're called the ordinary mode and the extraordinary mode. Here we go, ordinary and extraordinary. Just as sort of an indication of why this matters is that they travel at different speeds through the ionosphere. This is a rather exaggerated example because it's very low frequency. It's modeled beaming east from the UK with of course, we were at solar minimum back in, it's a bit different now, but solar minimum back in 2018. So that in this particular case, as I say, this is exaggerated because it's such a low frequency. The effects are greater at this kind of frequency, more visible. The O mode goes like that, and the X mode has quite a different path. If I could show you that in 3D, you'd see they're actually landing in significantly different places. So that's what FarLab does, enables you to plot the O and the X. Of course, when you actually want to know where the O and the X that arrive in a particular place, where my arrowhead is, where your antenna is, they will have gone through different paths. They probably were also launched at different angles, as a matter of interest. So I've built a very, very, very simple, it's an infinite sheet of ionization. It's about, well, I can change the thickness, and I've built a simple sort of raised cosine sort of shape that sits the extra ionization from the sporadic E on top of the E layer, the normal background E layer, based on the international reference ionosphere. I wish I could get rid of these blue blobs, but never mind. That will take too long to work out how to do that. So I built a model, and I'm going to describe a little bit about what it shows you. For these paths, these two paths from Hungary and Slovenia, mathematical model. So here's an example of the difference between the way that sporadic E reflects a wave and the normal E layer. I've chosen two different frequencies here. So here's the frequency, that's the frequency of the Hungary beacon. There's the sporadic E layer, a couple of kilometers thick. You can see it is a bend, it's not a sharp reflection, but it all happens over a pretty short distance. The lower trace is modeling the same path, the same source, and obviously destination, because that's where I am, at 7 megs. And here, the signal is reflected in the E layer, the normal E region of the ionosphere. As it happens on this particular day, it came out slightly lower, which makes a nice picture. You can also see the two characteristic waves shown separately here. That does happen on the sporadic E as well, but they're much closer together. But the point is that this spends about 7 times as long in the ionizing region. You can more or less ignore the rest of the E layer as far as 50 megahertz is concerned. It's there. It does have an effect, but it's a very minor effect. All the bending happens in the sporadic E, whereas at 40 meters, it's happening over a much that's longer distance, and that produces some interesting effects. Looking at these two signals, Hungary to the UK at the top, Slovenia to the UK at the bottom. This is a graph showing the angle of the path to the Earth's magnetic field. So the ray is greater than 90 degrees. It's a vector. So it's greater than 90 degrees to the Earth's magnetic field as it goes up. This is purely geometrical. But then as it bends through, it actually crosses the Earth's magnetic field at 90 degrees here. So it's at about 93 degrees as it goes up. By the time it comes down, the time it emerges from the sporadic E layer, it's something more like 75 degrees to the Earth's magnetic field. That's what distinguishes those two paths, Hungary and Slovenia, from the other paths that I was looking at. They happen to pass very close to perpendicular to the Earth's magnetic field, and that produces some different effects. So I've successfully modeled, you can see actually that the one from Slovenia, it's actually at right angles, very close to right angles to the Earth's magnetic field for a very long way. And that seems to produce different effects. So there's a couple of interesting observations in that. Firstly, I've had, when I'm modeling it, I can make a ray come back down to the ground. That's great. No problem. But I need to push the critical frequency, the density of the sporadic E layer, just a bit, maybe a megahertz higher than is actually seen on the ionosondes. That may tell us that there's something more going on. It's stated in the literature that for sporadic E, the maximum usable frequency can be maybe 1.5 or 2 times higher than would be simply calculated from for geometric considerations, allowing for the critical frequency, what they call the secant law. The difference between these two waves and between these two locations can't be just simply down to absorption, because absorption at 50 megahertz is a VHF frequency. The absorption in the ionosphere is low, and it's almost exactly the same for both the O and the X mode anyway. So you add those two modes, the O and the X, emerge from the ionosphere and eventually land at my antenna. on the way up, the power of the in my linear wave couples into the ordinary and extraordinary waves. But there's a slight difference between if it was transmitted horizontally, which I was told, no, sorry, vertically, which I'm told that both of these beacons are. It feeds the ordinary wave slightly more power than the extraordinary wave. What that doesn't tell me is why there's difference between those two. I have a suspicion, in fact, that the Hungarian beacon was actually running a horizontal antenna, which is something I want to follow up on. According to the modeling, the characteristic modes are on all the paths are very close to, on the way down to the receiver, are very close to being circular. And there's a representation on the right-hand side there of a polarization ellipse of an axial ratio about 1.05, which is close to both the ordinary and extraordinary wave, bearing in mind that the polarization of that wave depends only on the local properties of the ionosphere, the orientation of the magnetic field and the electron density. So it can be shown that if you've got two orthogonal circularly polarized waves, the tilt angle of the polarization ellipse when they add together, which they effectively add together in the receive antenna because they've traveled over different paths, the tilt angle can be shown to be equal to half of the phase difference. So I didn't know this until I'd run the modeling, that they're virtually circular. But what that means is that the tilt angle of the polarization ellipse that I observe can be shown I can derive the phase difference between the O and the X modes from it. And the point, as I said before, that the refractive index is slightly different between the ordinary and extraordinary. The paths they follow through the ionosphere are slightly different. The maximum usable frequency is actually slightly higher for the extraordinary ray than it is for the ordinary ray, which gives some potential for people wanting to maximize their DX performance on the sporadic E, much of interest. But the axial ratio, the shape of the ellipse, depends on the amplitude ratio, the amplitude difference between those two circularly polarized waves. You can imagine that if the right-hand one is 5 times as strong as the left-hand component, then the resultant sum of those two is going to be predominantly right-handed. To explain the observed variations, you need to be able to explain both the amplitude variation and the phase difference. I can explain the phase difference. Unfortunately, I can't get all the details of the complex refractive index, but by plotting the phase path length, it tells you the phase path length that the wave has traveled. And then plotting it across a fan of rays, which is what this chart shows. It shows that there's a consistent, on average, phase difference of about 1.5 meters. Now, when you think about it, 1.5 meters, 5 feet over a distance of 1,500 kilometers or what, 900 miles is actually a pretty damn small. And this all again comes down to the fact that they're spending a very short time within the sporadic key layer. So there isn't that much time, there isn't that much distance over which a large phase difference can build up. But nonetheless, it's there and it's consistent. So that phase difference, that path difference of 1.5 meters gives you a tilt angle of 45 degrees. So I mean,
Chris.
Yes.
You're saying the tilt angle plus 45 degrees. Are you able to eliminate the possibility that it's actually 360 plus 45 degrees or 720 plus 45 degrees? I'm not sure I'm following everything here, but
yes,
okay.
I'm going fast even now. Yes, no, you're absolutely right. From the observations, you can't, but from the model with a realistic thickness for the sporadic key layer, like I said, it's a couple of kilometers or maybe 4 or maybe 5. All of the phase difference is always less than a wavelength. But,
Okay,
but at a lower frequency in the E layer, then it could well be more than a wavelength.
Okay, thank you.
See what I yeah.
Okay, go ahead. I'd just like to wrap up in a few minutes so we give Joe plenty of time before,
Sure.
I'm not sure how many people want to stay late and can answer questions after 5 too. We can leave the call open for sure.
Okay, so just very quickly then, I looked at a particular case study. Here are the signals from Slovenia on the left, Hungary on the right. I did it on a particular day. They were the same day within 10 minutes of each other. And the reflection points of those two diamonds there. There are the simulation results on the right. So I can predict what the tilt angle is going to be from Hungary and the tilt angle is going to be from Slovenia by making assumptions about the height. I use the same height in both cases, but the thickness and the density of the sporadic key layer. So you can explain the phase difference by modeling the difference in thickness and density of the sporadic key layer. And as that changes, then the phase difference changes and the ellipse tilts. So that's where things stand. It's been applied. I can explain a key aspect of it, but I'm trying now to understand how I can model the amplitude difference between the two modes. And also there is clearly common mode fading as well, which must relate to the size of the blobs of sporadic E ionization. So that's where it's got to. You can have copies of this if you wish. Are there any other questions?
I'm sitting here kind of in awe because I mean you've done a very thorough scientific study, obviously, but the start of the whole thing was basically an amateur radio toolkit. Our antennas, coax equipment, receivers, and so on and so forth. They're very, I want to call them common, but very ordinary equipment. But then you've taken that so much further by doing the scientific analysis, and to many of us, we just get on the air, we turn the radio on, we hit the key or the mic button, and hope for the best. But with a little bit of knowledge and understanding, you can actually probably improve your results quite a bit.
Yeah, and believe me, I do that too. But I use circular polarization on 6 meters now.
There we go. Wonderful. Good. Any other questions for Chris? If he's got time afterwards, we can catch up with him some more too.
I just want to say that I did a work on polarization of the radio waves.
Right.
And the angle between radio wave direction of the B magnetic field, if it is closer to 90, things are totally different.
Yes.
We have it. Yes, we have it from. I have it from the model output also. And if it is more than 10 degree off from perpendicularity, then it is a lot more consistent with what we normally understand.
Yeah.
Exactly perpendicular, it is much more complex. So maybe I am interested in the work which you have. I will ask, or I will go through the papers which you have shared.
I agree with you. And I think that's what makes these two piles different from all the others that I saw, which were at different angles. Yeah. Well, and then if you want to follow up on that, Kuldip, please do.
Yeah, sure. Thanks.
Okay, great. Well, thank you very much, Chris. That was, like I say, it was kind of a soup to nuts explanation, but it was very, very thorough, especially in the time involved. And I think it will be nice for others to follow up with you after the call.
Fine.
Let's turn it over to Joe, K1YOW, who's got a perspective from the other side of the pond here in North America. Joe's had a lot of time and a lot of writings about 6 meters and whatnot. So let's give Joe an opportunity.
Can you hear the audio at all?
Yep.
Okay. I haven't run Zoom for a few years, so I was a little late because I was doing an update on everything, you know. Let me bring up the And then share screen, is it?
Yes.
Right, share. PowerPoint, there we go. And
Good.
if I
It's
bring it
working.
up- yeah, do I bring it up to full screen? Probably. It doesn't want to do that. Let's see, we'll make it this way. And this should go full screen. Okay, look good?
That looks good.
Okay, this is basically a stripped down version of what I did a few years ago. And basically, I'm also an old timer. I got licensed in 62 as a novice. This is an original call, so they're going to someday plant me with it. All right. Basically a simple station, a Kenwood, an IC 9700, an off-center fed dipole, and I got a log periodic up on the chimney, and that's my main antenna for VHF and UHF. So what got me started in this? A few years back, I wondering why you folks in Europe were having such great sporadic E, and we were having absolutely nothing in the United States. Day after day after day, I said, what on earth is going on? And my background is in reliability engineering, quality, communications, computers, modeling, that sort of stuff. So I'm very right-brained oriented, so I just had to figure this out. Basically, there was a PhD thesis, and they used this type of a methodology to find out what sporadic E was doing. They used satellite links, and they went around and watched stuff. And I won't get into any details of that here. But basically, they came out and said that it's a coupling process between the neutral atmosphere and the ionosphere. This I also agree with strongly. It's coupled and oriented with the Earth's magnetic field and is subject to tidal winds and things like that and meteor influx. So that's something that you probably all had before. Also due to solar inputs, solar tides, upper atmosphere stuff, vertical wind shear, which you mentioned earlier, all right? Meteor inputs, because metallic ions last longer than other types of ions, and a horizontal component of the magnetic field. So the wind shear basically sets up the sporadic E layer in a thin sandwich type of a deal. But this was what I really like. This comes from Jim Kennedy out in Hawaii now. And he said, basically, over the equator, there's the equivalent of a geomagnetic electrojet, all right? And what happens is what goes up must come down. So the sun is very hot over the equator. The ions tend to rise up. And as they get higher and higher, eventually lose some of the energy and they spread out and they tend to come down and sandwich into the mid latitudes. And then during the summer, that kind of shifts more to our north, all right? So we get more of the sporadic E effect in the northern hemisphere. So I really like that. I says that kind of explains why sporadic E is more mid-latitude type of phenomenon. So then they basically, this is what they put together from that PhD thesis. And basically you have the winter and summer, and you can see, of course, it's the more ultraviolet light, the more sporadic E you have. The spring and fall look pretty sparse. But what caught
Hey,
my
Joe,
attention?
Joe,
Go ahead.
we can't see the slides. We're still on the title slide. Are you?
Yeah, I don't know what happened then. Let's see.
Not advancing.
Now it advanced.
Yeah, yeah, okay.
Okay, now,
Thanks.
so you can't see if I bring them up? Can you see a slide at all?
It would say one says mid-latitude ES causes.
All right, so now if I go to full screen, does it still show it?
Doesn't change.
Okay,
You may
I'll
have to
just leave
share
it-
the
I'll-
entire screen as opposed to just sharing the window.
yeah, I'm just going to share this window then, I think. All right. If I go to the next one, does it show mid-latitude wind shear?
Yes.
Okay,
Yeah,
I'll
that's
just
there.
leave it. I'll leave it like this. I had it full screen. All right. So this is the Jim Kennedy's. Can you see that?
Yep.
Okay, good.
Yep.
This is Jim Kennedy's drawing, and it shows basically over the equator, you basically have a fountain effect where you get so much solar radiation right over the equator that things kind of rise up, and as they cool down and lose energy, they kind of spread out. And that causes kind of the E-layer sandwiching in the mid-latitudes. And I think, boy, that's just a beautiful picture of what's really going on. And during the, as I mentioned, during the summer, everything would then move to the left of the northern hemisphere, and we get more of the sporadic E up our way. But then during the PhD thesis paper, this is what was mapped out for the sporadic E. On the left side, you see the top winter, and then on the bottom summer, basically following the strong sun angles. And then during the equinoxes in the spring and the autumn, not too much going on. But that caught my eye, and I said, what's going on here? What's going on for us in North America? And that was part of my original question, was why was Europe having such great sporadic E, and we in North America were getting nothing at that year, all right? Well, North America is not a sporadic E hotspot, all right? So if it's not a hotspot, you know, we do have other things going on. We've also noticed that sporadic E happens also during certain types of storms. So now I started thinking, does weather have something also to do with it? All right, another few more variables into the equation. So I said, okay, if normal sporadic E is random, all right, what else is going on? Does weather have any kind of effect? All right. And then also in the back of my mind is, how on earth do we get transatlantic VHF communications? All right. And it's all kind of related. All right. And then can we see anything just using amateur radio, simple station and stuff like that? So here was a good example of, here's a transatlantic 6-meter opening. All right. Just, you know, the VHF gods were smiling on us that day. And since this, I've worked a lot, especially with FT8. FT8's like a communication mode, like trying to talk to the Voyager spacecraft. The bottom line is you get contacts you never thought were possible before. But anyway, transatlantic VHF, what is really going on? Now, back in the 60s, before they had all the computer stuff, they had, they used to publish on a monthly basis a set of charts. And with those charts, they would be the MUFs, and you would actually, by hand, on a great circle chart, work out propagation paths, and then use their predictions, all right, and find out what would, you know, what would be the best frequency to use to do communications. Well, my rule of thumb was basically a 2,000 kilometer path using the E layer, all right? And that's a key to what's going on in 6 meters with the transatlantic stuff, all right? Basically, every time we had, and I had a bunch of examples in here, every time we had transatlantic VHF communications on 6 meters, there were always 2 or more big storms in the North Atlantic, and those storms were always spaced within a single skip hop of each other, all right? So they were spaced within a couple thousand kilometers. And it happened over and over and over again. I had dozens of examples in the original talk. So I said, okay, now what's going on? Storms seem to have an effect on the E-layer ionization. So then I took another example and look, well, here's some E-layer paths going over to the east side of Italy, all right? What's really going on that? And I have more examples along these lines, but basically, right underneath the center of that E path, all right, was another strong storm system. So it looks like weather is also affecting everything here. So we always heard rumors that, hey, people working E-skip during hurricanes. That is if they have power. But okay, what's going on there? So I took a look, and we just happened to have Hurricane Matthew in that time frame. So here's Hurricane Matthew going into the southeast corner of the United States. All right. Basically, here we have some communications, but unfortunately, there was a lot of power loss. But the only skip was around the thunderstorms on the outer edge of the the hurricane. So again, weather had an effect on E-layer ionization. So then I said, okay, it just so happened that, if you remember, Europe had a lot of E-skip, all right, and a lot of sporadic E. The United States, when we do have it, in those maps, it was showing in the southern part, all right? It's actually following the magnetic field lines. You see, the magnetic field lines actually dip here, and the same strength of the magnetic field lines then go up and into Europe. So it's almost like a Goldilocks effect, where you have to have a magnetic field of a certain intensity, not too strong, not too weak, and the E-skip tends to be more prominent in that area. So now I said, okay, if weather had a little view and magnetics have a view, how come we have E-skip in the winter? All right, we've got no ultraviolet, very little ultraviolet from the sun. It should not work at all, right? The southern hemisphere should be having great E-skip on 6 meters, while we should be in a drought. So what's going on here, all right? Here's an opening, December 13th, 2017. Great opening up and down the east coast of the United States, especially in the Northeast. Well, it just so happens that a jet stream front is right there, all right? And the more I looked into this, all right, the more is showing that E-skip was forming on the eastern edge of an eastern moving jet stream. Here's another example with a few other spots going on. Same sort of thing, all right? So big low pressure systems and very strong jet streams. Above them, you can get sporadic E. Very similar situations. So there's a trend there. So it seems like when it comes to sporadic E, there's a lot of variables, all right? And jet stream boundaries seem to work, except we had a solar storm, all right? And everything was set up beautiful. I was getting ready to work sporadic E up and down the east coast of the United States. It was absolutely nothing, all right? And it was a huge jet stream trough over the United States, very strong. And it seems that this effect is negated when you have a magnetic storm, all right? So without the magnetic storm, with strong jet stream kinks, strong troughs, all right, you do get E-skip above the eastern edge of the trough, but if there's a solar storm in effect, you just don't get it. So I'm trying to figure out what happened there. Don't know, all right? Maybe the jet stream wasn't fast enough, but most likely the solar storm was the main thing, because it probably upsets the magnetic field gradients going around there, all right? And once those get upset, you don't have that nice line for the E-skip to follow. You don't have that horizontal component. It's getting all mishmashed up there. So putting on my reliability and quality and engineering area hats, I said, sporadic E is like one big design of experiment, and you have no control over any of the variables, all right? All right, you got solar UV, you got the magnetic fields that have to be in a certain strength, all right? And they can be upset by anomalies and disturbances. You have upper atmosphere shears and tides. You have solar storms and flares, all right? It's just one big mishmash, all right? So this went to a spot where I had no idea where I was going with it, all right? And to actually find out that weather also played a role. Our troposphere down here where we are, all right, had to play a role with what's going on in the ionosphere was a total surprise to me. I didn't expect that at all right? So sporadic E storms over North Atlantic. The storms have to be spaced within 2,000 kilometers, all right? And if you have more than one or two or three storms there, you can work more parts of Europe from North America. And it's always consistent, except when there's a geomagnetic storm in progress, all right? Fast winter jet stream boundaries, they seem to give us the sporadic E during the winter. So when there's sharp storms, that's when we get our sporadic E. So I was totally surprised by this. So this is just an average engineer playing around with ham radio, just seeing what's going on. So that's my quickie overview. Now let me see if I can unshare this.
Glad this is recorded. I'm going to go over it again.
Yeah, I don't know how to unshare it. Let's see. Screen. How do we
Yeah, I thought
unshare?
there was a red button that said stop sharing, but that I'm on a different OS maybe.
Yeah, I'm on Windows 10. It says screen sharing meeting, but I don't know how to get how do I get it up? Because when I did that, it took it down. Oh, here we go. What's this? Ah, there we go. I think.
I can stop it for you if we have to.
There we go. Yeah, why don't you stop it?
There we go.
All right, very good. Thank you very much.
Joe, thanks much. Somebody's got some questions for Joe, I'm sure. Very
Thanks for the
practical.
Thanks for the presentation, Joe. Very interesting. It's a line that I've been pursuing for a long while as a meteorologist, retired now. But I think the question I wanted to ask you, when you showed the map of the Atlantic with the two storms, 2,000 kilometers apart, were you showing surface winds on that map, or were they upper air winds, jet stream winds?
They were surface winds, and only from the point of view that you could see what was going on. If you showed the wind structure higher up, oh my God, it was very hard to see what on earth was going on.
Okay, thank you.
You're welcome.
I might
takeaway.
I'll finally interject that those transatlantic paths, that spacing of weather systems is very commonplace in the meteorological firmament. You know, that a mobile weather pattern will produce those features at roughly that sort of spacing. So I must agree that the FT8 is very great at identifying those weak marginal events, whereas the stronger sideband and CW events, which we used to hang our hats on, rare though they were, didn't give us too many examples to look at. But I think you're right. FT8 gives you a huge set of data to play with. That's good.
I know many of the HamSCIence presentations and some of the research and the plotting and stuff is involved the HF bands and not so much VHF, 6 meters and whatnot. So maybe this will incentivize a few more of us to, one, get on those bands, and number two, to look further into the research. That'd be a wonderful thing, I think. I mean, and the other trick is, of course, here in the States, many of us, I know there's a few on this call, live under restrictions, homeowners associations. You can't put up, well, some cases, no antennas at all, and certainly not very large ones, but 6 meter beams and whatnot are of a reasonable size. And I don't know if they could be hidden, but they're certainly less objective to some of the neighbors. So maybe more of us should be on that band for sure.
They could be quote unquote and TV antennas. They're about the same size.
Exactly. There, the OTARD, over the air receiving device laws by the FCC. If you can convince your neighbors that it's a TV antenna, you're in thanks to the federal government. Good point.
I must say, I've found within Europe on single hop stuff, going back to Chris's talk at the beginning, that vertical polarization doesn't close the show down, does it? So I've worked a whole bunch of squares within Europe, about 50 odd different squares, just using a 6 meter slim Jim made out of ladder line on a vertical fiber pole. So for single hop stuff, you can do a lot with vertical.
And that's just a sign that the polarization that comes down is not the same as the polarization that went up.
Oh yeah, that's actually that's the point. The people I were working, when I went online and looked on their QRZ pages, big sort of 6-8 element Yagis So yeah, well done them for investing in the station.
Hey guys, thanks so much for doing this today. This was interesting. I've got about 15 things now to go look up and study. But anyway, from my perspective, thanks for your time, gentlemen.
All right, good. Any more questions, or
Thank
otherwise
you.
we'll talk about next week real briefly. But Chris and Joe, thank you very much. I appreciate both your perspectives. I think the group does as well. And also thanks to Ed and Mackenzie, who did put some effort into publicizing our talk a little bit today. And that's why you see our membership is our viewership, I guess, is bumped up a little bit. And hopefully people also be viewing the recordings and stuff in the future once we get them put up on YouTube. That may take
Tell
a
your
week or
friends,
so.
right? Tell your
There you
friends.
go. There you go.
Yeah, thank you very much to the speakers.
Yeah, thank you.
Okay, well, next week we'll have another good speaker. You've heard from Jim Bacon already for a few minutes this afternoon. Jim's got a unique perspective because he's got one foot in the world of terrestrial meteorology and the other in space weather. So Jim will, I'm sure, enlighten us, continue to enlighten us on the subject. Any questions? Anything else for tonight? Otherwise, we'll call it a wrap for August 1st.
Thank you.
Thank you
All
very
right.
much.
Thanks everyone for attending. I look forward to seeing you all back next week. And if this is your first exposure to HamSci, don't forget our website, hamsci.org. We've got a lot of different projects going on and a lot of different bands and a lot of different ways for people to get involved. So please visit us and come back if you would. So with that, 73, and have a great evening, everyone.
7 days.
Hi, everyone.
Well,
Bye-bye.
Thank you.